Hi folks, well sorry that intro was totally misleading there, but I couldn't resist. What these actually are is a set of microchips that were produced in 1992 by Motorola in conjunction with University of Edinburgh, Scottish Enterprise and CompuGraphics, and these were built in a transparent plastic, and they've got extra large features on the chips so that you can have a look at them under a microscope. And there's a set of experiments to go along with this, or a sort of broad outline of some experiments in a datasheet. Now, I did actually already have one attempt at producing a video about these, and it took me hours, and after I edited it together I realised it was obvious I didn't actually know what I was talking about when I made that video. So for the last few weeks I've been back to my university textbooks, Principles of CMOS VLSI Engineering by Stragion and West, and I've been rereading a few of these chapters to re-familiarise myself with back what I learnt when I was at university, and I'm going to have another go, and I think I can explain, well, at least one of these four chips and what's going on. So let's have a try. So I've got the four chips here under my digital microscope, and each of the chips has got a number on it, and the numbers correspond to the datasheet. So this is chip 1, which is resistors and semiconductor materials, and the datasheet's got a bunch of experiments we can do with these, but I find the quite fascinating seeing how the wiring's arranged inside this chip, and you can see the little individual bond wires. I should get a pointy thing, and you can see how the lead carrier fits together, and you can see on here the individual bond wires hopping over onto the silicon die in the middle there. Well, that's chip number 1, which is resistors and materials. Chip number 2 here is a bunch of N-channel and P-channel MOSFETs. Chip number 3 is diodes and photodiodes. And chip number 4 here, the most complicated one, is our ring oscillator circuit. So, for today, we're just going to concentrate on chip number 1, take a look at that in detail, and see what makes it tick. Okay, so I've transferred chip number 1 onto a piece of breadboard, put on the Barlow lens to get twice the magnification out of this, so we're running somewhere around about 500-600 times magnification now, and you can see the bond wires here on this chip coming off from the carrier frame that goes off to the legs on the side there. You can see they've been bonded onto the pins there, and bonded onto the circuit board there. And the way they bond these wires is with a process called thermosonic bonding, which is kind of like ultrasonic welding, but they heat up these bond wires first to soften them up a bit and make them more compliant for welding, and that puts less strain on the silicon die when they actually connect them. But you can see here we're a Motorola chip, we're made in 1992. We've got all the different legs on the carrier frame individually labelled there. So we've got exactly the pin out for everything, and in the middle there you can see we've got our different resistor tracks. So we can see on this circuit board that the individual resistors have been labelled here. So we've got R1 in the middle there, which is connected between pins 1 and 2. And I'll just drop this out. See, I've got the datasheet here, and they've actually got this all labelled out on a diagram here that looks pretty similar to what we're seeing on the oscilloscope screen, on the microscope screen. We've got the space there where the Motorola logo goes. We've got our P well in the corner there. Got our wire going up to R8. So we all match up with what's on the data sheet. So I'm just going to zoom in a bit further and take a closer look at one of these resistors and see if we can identify some of the structures on this chip. This is me now at maximum zoom, and whenever I even slightly touch the desk we're going to get lots of camera shake here. Sorry about that, but here we are. I just want to have a look at R4 here, which is this long trace going from pin 4 that goes backwards and forwards over and over again down there and joins on to pin 13 and commons up with some others. So looking around this chip you can see that we've got 3 distinct colours here. We've got a silver layer, which is actually a layer of 99% aluminium and 1% silicon that's put down, and that's basically a connection layer. That's the wiring for the chip. The blue bit you can see, I believe, is silicon dioxide, which is an insulator, and they can grow layers of silicon dioxide on this chip while they're manufacturing it. And the black layers you can see are the layers of silicon that have been doped, and they dope silicon with phosphorus, boron, or I think arsenic, depending on whether they want p-type or n-type semiconductors. And I'm not going to go into the details here of actually how they make these microchips. There's plenty of videos there on that, but it's a process similar to how printed circuit boards are manufactured, or photographs are developed, or silkscreen printing for t-shirts, something along those lines. They put patterning masks on, they bombard the chip with either beam epitaxy, which is shining a laser beam at it basically, shining an electron beam at it, and they impregnate atoms into the structure of this chip. So we've got two distinct types of silicon there. We've got n-type silicon and p-type silicon, depending upon how the chip has been doped. So I did say that they provided a set of experiments with this, but the experiments are really very sparsely described here. It gives a brief description of the chip, which has 6 heavily doped silicon resistors with different ratios, and heavily doped silicon resistor built on a P-well, a metal film resistor, which is made out of aluminium, a lightly doped resistor with 6 peripheral contacts. And they suggest that things we might like to do are compare the electrical properties of p-type and n-type silicon, compare resistance at different ratios, and Hall effect, which is quite an interesting one. So I'm going to try and blast through these experiments and hopefully explain them so that people can understand what's going on. Let's get to work. So the first part of this experiment is going to involve measuring the resistance of these 6 different resistors we've got here, 6 or 7 different resistors. And I'll take you through the first one, and then I won't do the rest on camera, I'll do them off camera and see what we find. So at the moment I'm measuring the resistance between pins 1 and 2, which corresponds to R1 on their little circuit diagram. And for the utmost in accuracy, I'm using my 4-wire measurement on my new second-hand Keithley 6.5 digit desktop multimeter. And you can see we're measuring 1.6271 kiloohms. So I'm going to complete this for the rest of them and see what we get. So I've completed my measurements, and we've got values for the 9 different resistors to a ridiculous number of decimal places. And just to make things a bit easier for the explanation, I've just printed out an image of this chip that I've photographed, and I'll just have a quick talk through. So the first thing up here, R1, which is 1.16 kiloohms, is this patch of black here on the chip. And you can see at each end of the patch of black there's a metal contact to it that's aluminium, so that goes up to pin 1. Sorry, that one goes up to pin 2, and this one goes off over to pin 1 here. And the value for that resistor is 1.16 kiloohms, and I'm going to represent that with a 1K resistor. Now R2 is identical to R1 in every way. It's the same length, it's the same width, and it's also a p-type doping on the semiconductor, and as you probably expect, again 1.16 kiloohms. So we can see that R1 and R2 are both 1 kiloohm resistors. Now R3, this long black strip here, measured in at 2.33 kiloohms, which is basically 2 lots of 1.16, and as you'd expect, it's effectively our 2 1K resistors in series there, because we've got that one plus that one. So the ratio and the size of these resistors affects their resistance. R5 listed here, I've got a home invader, look at this. Come on, you out. So where was I? So R5 here is the same length as R3 there, but it's twice the width. And if we look, we see R5 is back to being 1.17 kiloohms. And what's going on there is basically we've got 2 1K resistors in series for the length, but because we've got twice the width, we've basically got 2 of them in parallel with each other, which is why we come back to 1.17 kiloohms again. So the same resistance value as R1 and R2, but effectively twice the current handling capability. And this goes on. This R6 here is half the resistance again of that, because it's twice the height here. same length, twice the width, so half the resistance. And again, this resistor here, which is just 580 ohms, again twice the height, twice the width of that one. So you can see that based upon the width and length of these things determines the resistance, and it doesn't actually matter how long they are or how wide they are. As long as the ratio of width to length is the same, you'll get the same resistance value. And this is called the sheet resistance of a material. And Dave Jones recently did an excellent video on this, looking at some hybrid resistors from a precision multimeter, and he gives a superb explanation, so I'm not going to go any further than that on our width versus length ratios. Now, there's a bit more going on here as well, because not all of these resistors are created equally. R4 here is a strip of aluminium, and as you might expect, with aluminium being a metal, the resistance is much lower, and we're coming in at just 33.5 ohms for this long track of metal going here, backwards and forwards, wiggling its way around, and we come out at 33 ohms. The other type of resistor we've got, most of these are P-type semiconductor, but we do have one down here, R8, this one, which is an N-type semiconductor. And you can see here, even though the ratio of it is 1680 microns by 30 microns, the same as R3, 1680 by 30, the resistance of this is much lower. And this is due to the intrinsic properties of N-type semiconductor, which I shall attempt to explain now. Now, hopefully you remember enough high school chemistry to remember what an atom is structured like. You've got a nucleus in the middle, and then you've got a number of outer layers, and each of these outer layers has electrons whizzing round and round it. And the first layer can only have 2 electrons in, but every other layer wants to have 8 electrons in it. So I've got 2 on the inside shell, got 8 on this next layer, and I've got 4 on this next layer, making a total of 14 electrons spinning around our nucleus. And that's because this is a silicon atom, which is element 14, which is why the company is called element 14. Now, what every atom wants is to have a full number of electrons in its outer shell. But silicon only has 4 electrons. So in an ideal world, silicon needs to borrow another 4 electrons from somewhere else. And what silicon does is it forms a lattice whereby each atom shares 2 electrons with its neighbour. And these 2 electrons that are shared gives this atom in the middle a total of 1, 2, 3, 4, 5, 6, 7, 8 electrons. So that atom's happy, and that's a very stable structure. And the same with everything else in this lattice. And silicon's a very stable and very uniform crystal. Now, pure silicon like this is actually a very poor conductor, because all of these atoms are perfectly happy with the number of electrons in their outer shells, so they don't feel the need to do anything very much. But if we dope this silicon by blasting it with phosphorus atoms at high speed, we can dislodge some of these silicon atoms and replace them with phosphorus atoms instead. Phosphorus is element 15 on the periodic table, which means that it's got 1 more electron in its outer shell. And what actually happens is you end up with a phosphorus atom replacing this silicon, and we've got kind of a spare electron hovering around there. And we'll replace that one as well, and that one ends up with a spare electron hovering around. And what happens now is this silicon's become a conductor, because if we apply a positive charge at this end of things and a negative charge at this end of things, these little electrons will drift towards the positive, and then more will come to replace them to fill up the gap that's left behind. So we get our current flowing, our electrons go off towards, our negative charges get attracted to the positive charges, and some current can flow. And silicon doped with phosphorus is what's known as an N-type semiconductor, because it's got a negative charge on it. The alternative is we could dope it with boron, and I've blasted a couple of silicon atoms out there and replaced them with boron atoms, which is only number 5 on the periodic table. So when it's in the silicon lattice, there's actually a hole where there should be an electron. And what happens is, when a charge is applied, this atom here actually wants an extra negative charge, and there's a load of negative charges over there. So what will happen is these links between the atoms will snap around and they change, and this hole will move closer and closer until it can get another electron to fill it up. And the same's happening with this one, so it'll steal an electron from over here and that'll come over there, and this atom's now missing one electron, but there's a load there, so that'll pull an electron in from there, and that way the charge can move through the boron doped p-type semiconductor as well. But whereas with the phosphorus doped semiconductor we've got these electrons just kind of floating around and it's very easy to get these electrons to move, with our boron dope, these holes in the semiconductor where there should be atoms, it kind of has to reform the covalent bonds between different atoms in order for the charge to flow. And that's a lot more difficult, and it basically makes a higher resistance path. The electrons aren't as mobile. This property is called electron mobility, and the electrons here just aren't as mobile because they're actually already in a reasonably stable chemical structure. They've got the right arrangement of atoms in their outer layers, that they don't really want to move quite so freely as these electrons up here that are just looking for a home. And this is exactly what we see in our resistance values. Our N-type silicon here, for 1680 by 30 dimensions, has a resistance of 870 ohms, but our P-type semiconductor with the same dimensions, R3, 1680 by 30, has round about triple the resistance. And this is just a fundamental property of silicon and the doping process. P-type semiconductor is not as conductive, and this is why it's actually a lot easier to find N-channel FETs and circuits using N-channel FETs than P-channel MOSFETs, because P-channel MOSFETs just don't conduct as well as N-channel MOSFETs. Right, so we've taken care of about half the experiments we can do on this chip now. We've checked out the different types of material for their different resistances. We've measured the difference between N-channel semiconductor, P-channel semiconductor and metal, and found the difference resistances in there. We've looked into sheet resistance and the ratios of these sheets of N-type, P-type semiconductor here and how they affect the resistance. We've got two more experiments left to do with this chip. This square resistor here, this square pad with the multiple contact points, will let us try out something called the Hall effect, where what we'll do is we'll set a charge travelling from one point to another, we'll put an electrical current through it, from there to there for example, and then we should find that when we apply a magnetic field to that, we can deflect some of the current off to these plates at the side, and we should be able to measure a voltage across this Hall sensor, depending upon how strong the magnetic field is next to it. So I'll plug that into the breadboard and see if I can get that working. So I've got my little circuit hooked up on the breadboard here. I've got power coming in on the red and black, which is red over here plus 10 volts, ground over here. So we're setting up a current flow this way across the resistor. And I've got my multimeter hooked onto this point and this point via pins 8 and pin 12 here. And I'm going to measure the voltage across there and see if I can influence that voltage using a magnet. So our voltage is fairly stable there, but when I come onto the scene with a ridiculously strong neodymium magnet, I've got to hold down these test probes because they're obviously magnetic, but you can see the voltage there has dropped down from 1.62 to 1.53, and if I reverse the polarity on the magnet, we'll push the voltage up instead of pulling it down. As long as I actually keep all the connections in place, but there we are, up to 1.63. So that's the Hall effect, and that's what's in a Hall effect sensor. It's just a square resistor. Right, the next thing we're going to show is something kind of fun with R3 here, this long thin one at the top. That's our 2.2k resistor, and it's the reason why chips are normally packaged in black plastic and why the Raspberry Pi, when it came out, had a problem with it being sensitive to flash photography because of the chip underneath it. And this is the photosensitivity of silicon. Because we've got all these atoms floating around, or the holes floating around, an electric field is not the only way we can get these electrons to move. We can also bombard them with photons of light, and that will help shift them along a bit as well and encourage them to move along, and the same applies to the holes in our boron doped p-type silicon. So I've set up my 4-wire resistance measurement across R3, which is this long thin one at the top here, 2.2k or thereabouts, and we'll just see what happens with that when I shine a torch on it. So at the moment we've got a fairly stable reading of 2.33 kiloohms there. Once I shine a light on that, you can see we've dropped down to, there we go, get it in the right spot, we're down to under 2k, as long as I hold the torch in the right place. Down to around about 2k, move the light away, we've got 2.3. So, hey presto, we've got a light dependent resistor. Amazing, another component just from printing silicon. But we're not done yet, there's one more thing to go. Okay, so now we're just hooked up measuring DC voltage across this resistor, and we've got no power supply whatsoever on this circuit board, we've just got DC voltage measurement. And what I'm going to do is I'm going to just shine a torch on it and see what happens. So I've got reasonable lighting in this room at the moment, and with just the room lighting on there we're getting round about 50 microvolts electricity produced by that. But if I shine a torch on that, bang, we're up to 7 or 8 millivolts there. Oh, nearly 10 there. I get it in just the right spot. Yeah, 10 millivolts across there, so it's a solar panel. Now technically we're still not finished with this chip even after all of this, because this will also exhibit diode and photodiode type effects. But as the next chip covers diodes and photodiodes, I'm going to leave that for a different video. I think this one will be quite long enough already, and I'm not sure how many people will actually watch it and understand it all. So if this one gets a good response, I'll go on and do chip number 2. It might take me a couple of weeks because I have to read up in a way that I can understand it all, which means pretty simple, because I'm only really good at simple things. But if people like this, let me know in the comments below, and I'll try and make the next chip. Anyway, thanks for watching folks, and see you next time. Cheers!